Hello everyone, I'm Yue Wu, an undergraduate student at Peking University. Today I'm going to introduce our recent work, Turboboosting Visible Light Backscatter Communication. This is a joint work with my colleagues, Pu Rui, Ke Nuo, Li Lei, and my advisor, Chen Ren. As the Internet of Things is turning into reality at a quick pace, billions or even trillions of ambient objects are expected to gain Internet access in the near future. Deploying such a massive amount of devices becomes difficult if you need to either wire them to power source or replace battery periodically. Today's wireless technology for IoT consumes tens or hundreds of milliwatts, for example, Bluetooth and LoRa, which hinders the development of devices with long battery life. Recently, backscatter communication has become an active research front, as it effectively offers merely orders of microwatts connectivity to small sensors, and hereby becomes a compelling communication solution candidate in the LTE era. Essentially, instead of active signal transmission, backscatter communication reduces energy consumption by signal reflection. Recent work shows it is possible to hitchhike the information over the ambient signals such as Wi-Fi, FM, and LoRa. However, radio backscatter will bring two potential issues when deployed for indoor IoT scenarios. The first, it interferes with normal daily traffic and exacerbates the spectrum crunch problem. And the second, its leakage through wall yields serious security and privacy concerns in room area networking use cases. Along the line but exploring a different medium, visible light backscatter communication presents an emerging and potentially better solution. It can leverage the existing infrastructures for communication purpose, specifically the dome light. The optical medium intrinsically addresses the RF interference, security, and privacy problems aforementioned. Like most backscatter systems, VLBC systems consist of many tool parts, called reader and tag. To establish a bidirectional communication link, reader first sends downlink data to tag with modulated light. We define this reader-to-tag link as downlink. The tag demodulates downlink data and prepares for the response. At the meanwhile, reader sends carrier signal and listens for response. The tag began replying by selectively reflects light with liquid crystal modulator, which is called a uplink. The final step is that reader receives the reflected light signal and demodulates uplink data. The downlink can easily achieve hundreds of kilobits per second because the photodiode receiver and LED transmitter can reach 1 GHz and 10 MHz respectively. In this case, the downlink throughput is mainly limited by power consumption design. The uplink, on the other hand, only reaches sub-kilobits per second data rate because of the slow LCM transmitter. You can think of a high-end game monitor that has 240 Hz refreshing rate, and that's approximately the speed limit of liquid crystal modulator. We come to a conclusion that the slow response of LCM as uplink transmitter is the bottleneck of VLBC. So here is a pair of LCD modules. Being charged or not, it can selectively let through the light or block it. If we apply square wave driven signal to the LCD, it reaches stable states with low frequency. But with higher and higher driven frequency, the response shrinks to only 4% of the total amplitude with 1 kHz. Thus, traditional OK deteriorates quickly above 250 bits per second, which is the 125 Hz driven source here. Have a closer look at the received signal, we can find that LCM has an asymmetric response. That is, the charging edge transition lasts only about 0.3 milliseconds, while the discharging edge lasts even longer than 4 milliseconds. The huge gap between them is never considered before for communication purpose, and thus the data rate is limited by the slow discharging edge despite the 10 times faster charging edge. If we want to improve the data rate, we would try two directions. The first one is designing advanced time amplitude modulation and coding scheme. Actually, there has been some works on this. For example, Miller coding finds a way in improving the data rate to 1 kilobits per second in time domain. For amplitude modulation, there is pixelated AM that use amplitude to carry information. The other direction is to explore more independent channels for parallel transmission, for example, using multiple light colors. Our solution includes two core technologies called DSM and PCOM. Delayed superimposed modulation improves data rate in a single channel by arranging multiple LCM pixels. Polarization-based quadrature amplitude modulation explores additional channels by exploiting the optical properties of LCM. The figure below demonstrates the signal in DSM view and PCOM view, which can work in a complementary way. In order to understand how DSM and PCOM works, we need to dig into the physical principle of liquid crystal modulator. We would start from liquid crystal shutter, that is a glass box with liquid crystal inside. The intermolecular force and electric force are competing each other. As a result, it rotates polarized light by 90 degrees in normal state while keeps the polarization angle in charged state. Then we add two pieces of polarizer in the front and behind, so that it becomes a liquid crystal display. It blocks the light when it's being charged and lets through the incoming light when not being charged. And this is how LCD monitor works. One more step forward, we come to the first design of VLBC, which includes a retroreflective fabric that can steer the light back to source. The same as LCD, it absorbs all incident light when being charged. The final step comes our liquid crystal modulator that removes the front polarizer. In charged state, it retroreflects vertically polarized light, and in normal state, it retroreflects horizontally polarized light. In other words, LCM can manipulate the polarization of retroreflected light. The takeaway message here is that LCM can selectively reflect 0 degree or 90 degree polarized light, and because of the internal competing forces, the charging edge is 10 times faster than discharging edge. Let's consider the first attribute. How can we explore more channels with it? The Malus law tells us how a polarized light is attenuated when passing a second polarizer. If we use a liquid crystal modulator with 0 degree polarizer, called a ILCM, the received signals are shown here. Despite the charging and discharging transition, there are two stable states. The same for a LCM with 45 degree polarizer, called a QLCM. Given the fact that light intensity is linearly superimposed, if we use both ILCM and QLCM to send 2 bits information, we can get 4 stable states in the received waveform. Those stable states form a constellation plane of in-phase and quadrature channel. Furthermore, if we use binary divided pixel error ratio for ILCM and QLCM, it forms a higher order constellation. In real-world deployment, an angular misalignment between reader and tag is very common. We find that a physical rotation of theta reflects 2 times theta in the constellation plane. However, the distance between symbols does not change. This attribute shows that, with polarization-based QAM, an angular misalignment does not deteriorate performance. This is our final design of PQAM. It explores 2 independent channels for parallel transmission, while at the same time it tolerates angular misalignment without performance loss. We define the number of points in the constellation as PQAM order p, and PQAM improves data rate by log p. Let's go back to the attributes of liquid crystal modulator. We then look at the second attribute. Charging edge is 10 times faster than discharging edge. LCM is a nonlinear module because the same bit inversion does not result in the same signal difference. We need to keep LCM response deterministic and controlled in order to demodulate data successfully. The basic idea is that we give enough time for LCM to go back to its normal state so that it behaves the same every time. We arrange the slow discharging edge in a fixed time slot and fire the faster charging edge at multiple time slots. We can see the different responses of those 4 code words. This design is quite easy for demodulation. Just take samples at those red points. The basic design shares the same time slot for discharging edge to improve the data rate. We define the number of LCM pixels as DSM order L, and it improves data rate up to 1 divided by t. However, this convergence is very slow, and we cannot use a very large DSM order L because the total signal strength is usually a design constraint. With a larger L, each bit will result in a 1 divided by L of the total amplitude, which would be too small to recognize. We try to make DSM even faster by overlapping the discharging edge and charging edge. The blue discharging edge follows each red charging edge without waiting for others. The received signal behaves like this. A naive demodulation algorithm detects if there is an ascending edge at those red points. However, this naive solution does not work when combining with SIGCOMM, which will be discussed later. This is our final design of DSM. It interleaves multiple LCMs and improves data rate by 1 divided by t, totally eliminating the effect of slow edge. In order to predict the received signal, we suppose that the pulse response of each LCM is identical and limited in a time range from 0 to w, which is exactly a DSM symbol duration. Given the noise signal and transmit bit sequence, we have the expected receiving signal below. In this way, we claim that DSM design is essentially a PRS scheme, which introduces inter-symbol interference that spawns L symbols. We differ from conventional PRS systems that LCM is a very constrained, nonlinear transmitter. It's quite straightforward to combine DSM and SIGCOMM. We send SIGCOMM symbol at each DSM slot. To give you a brief illustration, here is our tech hardware design that sends 8-order DSM and 16-order SIGCOMM signal. You can see that each pixel returns to its normal state before trying to send the next symbol. Next, we go to the receiver design. It has 3 parts. Preamble design helps to detect packets and do frame alignment as usual, while it does one more thing to correct the SIGCOMM rotation. Demodulation design includes a optimized decision feedback equalizer for near optimal performance. Channel training in the end handles subchannel heterogeneity from different LCMs to assist the demodulation. Our demodulation design takes ideas from both the optimal solution and the computational effective one. MLSE has optimal performance, but even optimized Viterbi algorithm has a complexity of n times p to the power of L. A typical setup of p equals 16 and L equals 8, the constant is about 4 billion, which is too large for real-time demodulation. DFE has a small computation complexity but suffers from error propagation. Our solution is a k-branched DFE, which stores at most k branches. Given a sufficiently large k, it is equivalent to the optimal MLSE. An appropriate k value could reach both near optimal performance and low computational cost for real-time operation. Here is an example of 16-branched DFE. Given the received signal, we find those candidates that best emulate the received signal. By keeping the candidates to at most 16, the computational cost is bounded. Keep doing this for the rest of the packet, the demodulation result is the best one among all candidates. The modulation process needs accurate model of LCM to reconstruct the expected received signal, but we find several defects of the simplified pulse response model. First is the interference between ILCM and QLCM. Although they have no interference in stable state, the transition of charging or discharging results in a partially polarized light, and thus it has interference across 2 channels. The second is tail effect that previous bits actually affect the current pulse response. Although the 66% difference seems small in the whole packet, it affects a lot within the DSM time slot, where DFE used to judge the current symbol. Third, location and LCM heterogeneity affect the pulse response. This comes from errors in manufacturing process and also parameters like temperature. These defects lead to the failure of our early experiment, and thus we design a channel training process that takes them into account. The channel training design is composed of 2 parts, a offline channel training that takes hours to collect, which results in a set of reference spaces, and a online channel training solving the coefficients of those reference spaces and reconstructing responses for individual LCMs. We developed the customized reader and tag hardware to verify our design. The tag is composed of 4 LCMs with retroreflective fabrics behind. It supports up to 8-order DSM and 256-order SIGCOMM. It is also optimized for power consumption. Reader includes 2 front ends receiving in-phase and quadrature polarization light signal, and a back end using voltage-controlled amplifier for a wide working range. It can connect to PC with USB ports streaming live data. Our real-world experiments use a default setup of 4 watts reader LED power and a ±10-degree field of view. We send 30 packets, each 128 bytes. The default data rate is 8 kilobits per second with 8-order DSM and 16-order SIGCOMM. Our experiments include speed error rate results to test the physical parameters and a macro benchmark to evaluate software parameter selection. We also have emulation results for massive deployment and extended usage. The working range is 7.5 meter for 8 kilobits per second and 10.5 meter for 4 kilobits per second, which satisfies most indoor IoT scenarios. Thanks to the carrier signal design, our system behaves consistently regardless of the ambient light condition. There are 2 kinds of angular misalignment, as illustrated here. SIGCOMM tolerates raw angular misalignment theoretically, which is verified in our experiment. For the yaw angular misalignment, our system tolerates at least ±40-degree misalignment. DFE performs worse than the optimal Viterbi ones, while our 16-branched DFE performs near optimal with low computational cost. In channel training, if we consider no previous bits, the system would fail. With 2 bits considered, it is nearly close to 3 bits ones, and thus we use 2 bits version for near optimal performance. In the emulation of higher order modulation, we reached 32 kilobits per second under a 55 decibel SNR restriction, which corresponds to a 3.5 meter distance. Coding helps to improve output in a wide range of 22 decibel. In conclusion, we revisit material and optical properties of liquid crystal modulator. Based on that, we propose 2 novel modulation schemes that exploit LCM's asymmetric response and polarization manipulation capability. We pushed the data rate of visible light backscatter communication by 8 times in real-world experiments and 32 times in emulation.